the precipitation law. A precipitate. That's a word that's used for an insoluble salt that forms. That's a precipitate. That's a reaction, a double replacement that produces an insoluble salt is called a precipitation reaction. And for all of them, we are going to learn a procedure that gives you a molecular, a total ionic, and a net ionic equation. And I do have to assume you remember this from your previous class. Sort of. Right? Okay, so dig deep. Let's do one of these examples. In double replacement reactions, you absolutely must have a weak electrolyte as a product. That's why it's so important that you know your lists of weak electrolytes. Because you absolutely must know at all times what's a strong electrolyte and what's a weak electrolyte. So that when you're presented with an equation, you are able to find among the products a weak electrolyte. If you don't find a weak electrolyte in the product, you erase the whole thing and answer what? No reaction. Let's go through one and then let's explain it. So the first one is a first double replacement reaction. How do I know it's a double replacement reaction? How do I know? So an acid and a base, so what's that? A neutralization, correct? And how do you do the double replacement? What did we talk about pluses and minuses last time?
Positive and negative.
The positives, we have them on the left and the negatives are on the right. So this is my positive area, that's my negative area. Is that fair? So when I mix that positive one with this negative one, what am I making? Water, HOH, right?
Yeah.
And this negative with that positive, I'm making a salt, aren't I? And I cannot make up my own chemical on the other side. I have to maintain those charges. What charge is that titanium? What charge is a sulfate?
-2.
What is the formula of the titanium sulfate that is formed on the right-hand side? Ti? Ti what?
2.
What's the charge on the titanium? What's the charge on the titanium? +4. What's the charge on the sulfate?
-2.
How many of each do you need for electrical neutrality? 1 titanium and 2 sulfates. Okay. Where does the subscript go? On the sulfate. And with a parenthesis, oh my, before that looks like a 42. Is that correct? Okay. What happens if you put a substrate of 2 on the titanium? You have a total of +8. And that would not be electrical neutrality. If something is charged +4 and the other thing is charged -2, how many of each do you need? 1 of the +4 and 2 of the -2, because these are real counts. This means 1, 2, 3, 4. And if you have only 2 of these, you don't have electrical neutrality. So you need 2 of those. We good? So, step number 1, cross the items and make sure you write the chemicals correctly on the right-hand side with the subscripts, just like we did. Is that fair? Okay. Second item, find a weak electrolyte. Because your 2 choices are, you're either going to find a weak electrolyte and go through with the balancing and everything, or you're going to find strong electrolytes, erase the whole thing, and say there's no reaction. Those are your choices. So here we go. Now that I've crossed the charges and predicted my products correctly, Is titanium sulfate a weak electrolyte? Is titanium sulfate a weak electrolyte? Wait, don't tell me. Where do I look for weak electrolytes?
The list.
On a list. What are the weak electrolytes? Weak acids, weak bases, insoluble salts, gases, and water. Oh, look, water. Did I find a weak electrolyte?
Yeah.
You betcha. Does this reaction occur as written? Yes, it does. Why? Because I found a weak electrolyte among the products. Next step. Place the little parentheses on your products. Usually, the given starting materials will already have them. So number 1, cross the charges. Number 2, write the chemicals correctly. Number 3, get the parentheses going. We good? What you gonna do for this one? Use the little scheme we talked about. Where's that little scheme at? How do you know? According to rule number what? Find it for me. Where are you going to look for the solubility of a salt? In the solubility rule. So, what do you got? All solubles are soluble except for lead, strontium, and barium. Oh, but that's titanium. So what do I put? So what do I put? My choices are aqueous or solid. And seeing as though that's a salt, it's either a soluble one or an insoluble one. According to the solubility rules, it is soluble, aqueous. Any doubt? Any doubt? You sure? Okay. The more examples we do, and actually, in this case, believe it or not, the faster we go through more examples, the better off we are.
Right next to the water, what's the parentheses there?
Liquid. No. Some weak electrolytes are going to be aqueous, because all aqueous means is what? Soluble in water. Aqueous does not mean strong electrolyte. Okay? Next step. Balance it. Why not balance it first? Because you might be wasting your time. If you balance it up front, you might have to wait until later to find out that the reaction doesn't actually work, and then you wasted a lot of time on a test. So the first order of business is to cross those chemicals, write them correctly, and find out weak electrolyte. Only then, when you know that that reaction actually occurs as written, then go ahead and balance it. You good? Okay. So what does the reaction actually look like? H2SO4 aqueous plus TiOH4 aqueous going to water liquid plus TiSO4 aqueous. And believe it or not, the harder part's already done. Because the decision-making process of having found a weak electrolyte is actually the more challenging one. Look what happens now. Now it's just a regular balancing. So, balancing equations. How do you balance a combustion equation? CHO. With a decomposition, we already saw an uneven rule from last time. This is another helpful hint. Polyatomic ions first. And you do them as a package deal. In other words, whenever I see this sulfate, I actually don't take it apart. And I never tell myself that this is going to be 2 oxygens, that this is going to be 2 sulfurs and 8 oxygens. I don't do that, because that blows up atoms in every direction, and I'm forever counting, oh my God, 12 here and 9 there, oh my gosh. When you see that there is a polyatomic ion that survives the reaction intact, in other words, exactly this is an SO4 sulfate, and exactly here it is again, keep them together and use them as as a single item, as a package deal. Polyatomic ions first. Here's another polyatomic ion, a hydroxide. It sort of survived the reaction in the water, but that's harder to see. Because don't ever forget that what's water if not HOH? One equivalent of acid equals one equivalent of base. So polyatomic ions first. How many sulfates are here? Two. That makes me put a 2 there. We good? Okay. So what do I do now? If I put what? A 2 or a 4? A 4. Why? Because when you're in the business of forming a water molecule, the fact that you did polyatomic ions first forced you to put a 2 here. That means that you have how many H's? 1, 2, 3, and 4. How many OH's do you have here? 1, 2, 3, and 4. How many water molecules do you make out of 4 H's and 4 OH's? 4 water molecules. That's why that number's a 4. In acid-base reactions, you count your water last. And it's the same number of hydroxides because it's a 1-to-1 basis. 1 equivalent of acid equals 1 equivalent of base. So 4 H pluses meet 4 hydroxides to make 4 water molecules. Is that fair? Okay. Now that it's balanced, the next step is to write the total ionic equation. The total ionic equation. The molecular is the balance. The total ionic equation is written by following your own rules. Break only the strong electrolyte. Leave the weak alone. Break only the strong electrolytes. Leave the weak alone. Of course you would only break the strong electrolytes because that's what it means to break a strong electrolyte. That's what it means to be a strong electrolyte because they ionize 100% in solution. That's the definition of a strong electrolyte. So here we go. Now we play strong electrolyte, weak electrolyte. Strong electrolyte, weak electrolyte. Strong, how do you know? Strong acid, it's on the list. Strong electrolyte, weak electrolyte.
Weak. It's weak.
Where do I look for this?
On the list.
Where do I look for this?
The list.
What list? The list of what?
Oh.
I know like 4 lists. I know a list of strong electrolytes, I know a list of weak electrolytes, I know a list of strong bases, I know a list of weak bases. On which one of those lists do I look for that item? On the list of, what kind of an item is this? It's a say base. Base. So now I have to look at it where?
Strong bases.
In the list of what? In the list of bases. Correct? I have to now determine whether titanium hydroxide is a strong base or a weak base. Where do you look? On the list. Is titanium hydroxide a strong base or a weak base?
Weak.
Don't look at me, look at your list.
It's a weak
That's what we're
base.
doing. We're organizing information. What are your strong bases? Name them. 1A hydroxides and 2A hydroxides except beryllium and magnesium. Is titanium hydroxide on that list?
No.
Therefore, it is what?
A weak base.
Go ahead. Go ahead. Please, somebody raise your hand. Make my day. Raise your hand and tell me. But isn't it AQ a strong electrolyte?
No.
Go ahead. Oh, I dare you. I double dare you. Oh, I double dare you. Okay. You understand? Where do we look for bases?
The
On
base.
having a Q doesn't mean it's a strong electrolyte.
Que
A
me da mucha
lot of
risa.
weak electrolytes are soluble in water. We good?
Voy a grabar todas las
So here we go. Strong electrolyte, weak electrolyte. What?
week.
Weak electrolyte. Strong electrolyte, weak electrolyte. How do you know? Because we already determined that was a soluble salt. So this is a strong electrolyte. So number one, cross the charges, make your compounds. Number two, find a weak electrolyte. If you have one, balance the reaction. Next, label strong electrolyte, weak electrolyte. We good? This one is called the molecular equation. The molecular equation is nothing other than the balanced equation. That's all it is. And now we're going to write the total ionic equation. The total ionic equation is written based on this criteria. Break only the strong, leave the weak ones alone. Okay? So, strong electrolyte. Do I break it? Yeah, that's what I do. That's what strong electrolytes do. They break apart 100%. So, 4H plus aqueous plus 2SO4 minus 2 aqueous. Plus, do I break that? Nope, I leave it alone because I've determined, according to my definitions, that to be a weak electrolyte and I leave it alone. Do I break up my water?
No.
That's my product. If I break up the water, then I got another shot. Plus, do I break this one?
Yeah.
Yep. So Ti plus 4 aqueous plus 2SO4 minus 2 aqueous. Because you owe me the coefficient, the charge, and the parentheses. That is the total ionic equation. That's the total ionic equation, where you break the strong and leave the weak alone. The net ionic equation is written by canceling spectator ions. What are the spectator ions? The ones that do what? That appear exactly the same on both sides. And the name is very, very apt. A spectator ion is something that doesn't do anything. So which ones are spectator ions here? The only thing is that sulfate. And you rewrite everything that's left. So the net ionic equation is 4H plus aqueous plus TiOH4 aqueous going to 4H2O liquid plus Ti plus 4 aqueous. And the sulfate cancel. That's an ionic. Next. This one. Step number one, cross the charges. Write the chemicals on the other side. So what do I write on the other side? If my positive side takes up residence with my negative side. Potassium, how do I write that? K, NO3. And is that the correct formula? Is that the correct formula? How do you know?
Potassium is one.
Because it's a plus one and a minus one. Is that right?
Yeah.
Why is titanium?
Why is what? I'm sorry.
Titanium.
Because it's a soluble salt.
Yeah, but then you break it down. So shouldn't it be solid?
That's exactly the essence of being a strong electrolyte. Go back to your favorite electrolyte, and let's put that teaspoon of salt in that water. Let's put that teaspoon of salt in that water. What happens during a dissolution? What happens during a dissolution? What happens during the time that a strong electrolyte, what happens when a strong electrolyte goes into water and it gets dissolved? What happens when last class? What happened last class? That the water came in and destroyed the solid matrix, the crystalline structure. And when they separate, they are now solvated individual ions, and that means that they are Na plus aqueous, because now they're being solvated, and Cl minus aqueous, because they're being solvated. This is a salt going into water that you determine to be a strong electrolyte. So it ionizes 100%. So when I look at my having determined that this was a strong electrolyte, according to the place where I look for strong electrolytes when they're salts, item number 5 in the solubility rules, I immediately classified this as a soluble salt. What does that mean? That this procedure is in effect at all times. And therefore, these are aqueous ions floating around a beaker. That's why it has to be AQ, because it's the product of a strong electrolyte ionization. What's the other product? Potassium nitrate and lead. What the hell is that? And how do I write lead acetate from this particular lead with that particular oxidation number? PB parenthesis C2H3O2 2. And now the biggest job of the day, we get to play.
I've got weak electrolyte.
So, is this a strong electrolyte or a weak electrolyte? Where are you going to look? When you're determining whether something is a strong electrolyte or a weak electrolyte, where are you going to look? If you're going to look for a salt, what are you going to look? In the solubility rules. And KNO3, is that a salt? Yep. So where do you look? In the solubility rules. So, strong electrolyte or weak electrolyte? Strong. Strong. An alkaline metal salt. Rule number 1 or 2? The very first one, right? The first two are about ammonia and 1A metal, but they always are. What do I put behind here? What do I put behind here? AQ is the state of matter that goes to soluble salts, strong acids, strong bases, sugars, weak acids, and ammonium hydroxide. All those things take AQ. That's a soluble salt, AQ. Lead acetate. According to rule number 1, and where are you looking? Solubility rules, because it was a salt. And what happened? What happened? Where's that at? It's rule number 3. And that's a pretty blanket rule, isn't it? Nitrates, chlorates, perchlorates, and acetates are soluble, period. All of them. Soluble, period. So what does that tell me about my lead acetate? Aqueous. Now that I've got my parenthesis, let's play strong electrolyte, weak electrolyte. Because in order for a reaction to occur, I must have a weak electrolyte as a product. Is this a strong electrolyte or a weak electrolyte?
Strong.
Is that a strong electrolyte or a weak electrolyte?
Strong.
Do I bother balancing this turkey? No. What are you going to do? We good? Okay. Okay. Next. Let's work a little faster. Tell me what the products are on the other side already. Come on. CA. Subscript for the CA. String 3. And PO4 parenthesis 2. And we'll look at the parentheses in a second, the state. And what's on the other side?
H4.
H. Well, what's the H going to take up resonance with?
The
The
salt.
SO3. And that charge is what? Negative. The SO3 is a minus 2.
Minus 2.
So how many hydrogens do I need?
2.
Okay? Crossing the charges and writing the chemicals correctly on the other side. The chemicals are written correctly from the charges on the other side. I never look at the subscripts to assume then I'm gonna put the same subscript on the other side. Because you have new partners. It's a new set of rules of pluses and minuses. It's a new set of rules of pluses and minuses. So I have to be able to write the correct chemicals on the other side. Take 30 seconds. Do you have any doubts whatsoever? Are you sure? Okay. Let's play strong electrolyte, weak electrolyte. What do you got? What's this? It's a salt. Where do I look? Solubility rules. So, soluble or insoluble? Insoluble. Remember calcium phosphate? The major components of our bones. It's better that we're not soluble? Yeah.
Why do you put the 2 after PO4?
Electrical neutrality. How many of each do you need? Ca is a +2. So the subscript becomes 3. And the PO4 subscript becomes a 2. Because that's a real count. I'm going to need 3 of these. Because PO4 is a -3, and the only possible electrical neutrality arrangement is to have 3 of these and 2 of those. The only possibility. Remember this? Same thing. Right? Insoluble, right? So what do I put behind here? S for solid. It's an insoluble salt according to the solubility rule. Hey, what do I put here? What is that? And where do I look? That's a, is it a strong electrolyte or a weak electrolyte? It's weak. Why?
It's
It's not on the list of strong. So, wait. What do I do? What do I do with weak acids? What do I put? Oh, okay. AQ. Because what? Because what? AQ doesn't mean strong electrolyte, it just means soluble in water. I will always know when something is a strong electrolyte because I memorized a list. Strong acids, strong bases, soluble salts. Those 3 things are strong electrolytes. Weak acids, weak bases, insoluble salts, water, and gases are all weak electrolytes. Regardless of what they say in a parenthesis behind them, I will always know that item is not on the list of strong acids, and it is therefore a weak acid. It might be soluble in water, that's not your fault. But that's why it has an AQ behind it, and it's still not your fault. We good? Okay. Does this reaction occur as written?
Yes.
Why? Because I found weak electrolytes in my product. And this time I got lucky, I got 2 weak electrolytes. So that reaction is a big time yes from the left to the right. So what's my next move? Balance it. Because now now that I know that it happens that way, I'm gonna go ahead and balance it. What do you got? Polyatomic ions first, right? So I'm guessing that's why you're looking over here and saying, hey, there's part of 2 in front of that thing. And then what? Will that fix it? That fixes it?
Yes.
Let's see. 3 calciums, 3 calciums. 3 sulfites, 3 sulfites. 6 H pluses. 6 H pluses. 2 phosphates. Great. Is that good?
Mm-hmm.
Okay. And all because you did polyatomic ions first. If you get into the business of multiplying things out and saying, oh my gosh, 8 oxygens and 3 oxygens, 8 and 3, 11 oxygens, oh my gosh, you're going to take 10 hours to balance these equations. When you've got polyatomic ions present, Treat them as a package deal. Don't break them into individual ions. Treat them as if they were a single thing.
Do we always do the reactants before the products?
No, you can do whatever you want.
I have a quick question. The list of the weak bases was 1,8-hydroxide, 2,8-hydroxide.
Except beryllium and magnesium. Except beryllium and magnesium. So this is the molecular. That's a molecular. How do I do a total ionic? Break the strong and leave the weak alone. Is that fair? So strong electrolyte, weak electrolyte. That's an insoluble salt. Strong electrolyte, weak electrolyte. It's an insoluble salt.
It's weak.
Strong electrolyte, weak electrolyte. Where do I look? The list. Is that on the list of strong acids? Therefore,
It's a weak.
weak electrolyte. Strong electrolyte, weak electrolyte.
Weak.
It's an insoluble salt. Strong electrolyte, weak electrolyte.
Weak.
Do I break anything?
No.
Damn, there you go. That's the net ionic equation. We good? Can't break anything. Not your fault. Is that fine? You sure? Okay. Minor thing. Minor thing. Not your fault. Not your fault. But unfortunately, you have to be responsible for this. You see this one? You see that one? There's something you have to know that I haven't told you. And it occurs, I swear to God, not your fault. And it occurs with two acids that are formed as products sometimes. One of them is carbonic acid. One of them is carbonic acid. The other one is the acid we just made. One of them is carbonic acid and the other one is sulfurous acid. There is something you have to know about these that I haven't told you. Carbonic acid is actually a very common acid. It's actually very important in biological systems. Very important. The buffer system and the equilibrium that takes place with carbonic acid in living organisms, it's extremely important, and you're going to see a lot of it in the biology classes. But having said that, what we know about carbonic acid up to this point is that it's a weak acid because it's not on the list of strong, and that's true. So do we agree on that at least? Yeah? Okay. Here's something new that no one told you before. Carbonic acid doesn't actually exist. Not your fault. Because under this atmospheric conditions, under these planetary third rock from the sun kind of conditions, carbonic acid decomposes 100% and spontaneously into CO2 and water. So carbonic acid, as soon as it forms, bubbles right out of solution. And the bubbles that you see are that CO2. Not your fault, I swear. But you're responsible for it. So when you look at exercises such as this one, when you produce either sulfurous or carbonic, you're actually not done yet when you get to the net ionic equation. If it's sulfurous, follow the pattern. What would the products be?
I saw two and it's precipitate.
And there's nothing I can do about this, I swear, and not your fault. So when you end up having produced one of those two, and you get to the net ionic equation, you're not done yet. You are not done yet. You're going to have to destroy this one into SO2 and water. My advice is to never do that in the beginning. Because if you do that in the beginning, it's going to be a lot harder to balance the equation. So you are aware of it, and you say to yourself, oh look, This is one of the two acids that are going to decompose later. And you finish the problem all the way to the bottom. The molecular, you balance. The total ionic, the net ionic. And at the very end, then you do the procedure. So you now are going to rewrite this item with the decomposition of that particular acid. And you rewrite 3CaSO3 solid plus 2 phosphoric acids, soluble in water, but weak electrolyte, because I know it's a list of strong acids, and he ain't on it. So that's a weak electrolyte. Is going to be Ca3PO4, calcium phosphate, the big time, famously insoluble in water. And break it apart. And now you're done. What's a parenthesis for the water?
3SO2.
And this guy, that's a gas. If it were carbonic acid, it'd be the same thing. And you're going to run into them. Coming soon, possibly, to a 1045 lab exam near you. The carbonic acids and the sulfurous acids as products. Yeah, but you look at it for the first time, and you go, how was I supposed to know that? That's true. I agree. You look at it, and you go, but then after that, the second time you see it, you put your eyeballs back in your socket, and you say to yourself, self, I've seen that before. It's that whole learning thing. Yeah. What? I did. Where's the signing sheet? You guys keep passing around the signing sheet. I know. Don't worry, you'll sign it later. All right, here we go. Let's do the next one. Let's do the next one. One more. Do one more before we go. Do one more. Let's do one more quickly. We have like 3 minutes. Let's go. Let's do the bottom one. I want to do the bottom one. Because this one is an acid-base reaction. We can do that one later. But we'll do that one on Monday. Let's do this one first. Let's go faster. Faster. What do you do? Fe2, SO3, 3, plus cesium chloride. And now I need to put my parentheses. Who else has to sign the attendance sheet? Alright, what are you going to do for the parentheses? What are you going to do? Where are you looking to put the state here? What is that? Salt. Where do you look for salt?
Solubility rules.
Solubility rules. You're looking for salts, whether something is soluble or insoluble. So is that soluble or insoluble?
Soluble.
According to rule number what?
It's insoluble.
So therefore, that's an S. How about cesium chloride? How about cesium chloride? What are you going to do for that one? Soluble, according to rule number what? 4. You know, I wasn't going to get past rule number 1. I wasn't going to get past rule number 1. Why? Why is that? Because cesium is a 1A metal. All soluble, so 1A metals are soluble, period. So, what's this? Aqueous. Does this reaction occur as written? Yes. How do you know? You have a weak electrolyte on the product. Do I bother to balance it now? Yes. So, an odd even rule, 3 of these. If I could put 2 of these, I think, it's a 6, and if I stick a 6 here, I'm done. Is that correct? Yeah? Okay. Break the strong electrolytes, leave the weak ones alone. Is this a strong electrolyte or a weak electrolyte? Soluble salt. What is it? Strong electrolyte. Strong electrolyte, weak electrolyte. Strong electrolyte, weak electrolyte. Where do you look for this one?
It's strong.
It's a salt. Where do you look for it? Solubility rules. What's the first solubility rule? One A metal salts are soluble, period. So therefore, that item is what?
A strong
A strong
electrolyte.
electrolyte. Strong electrolyte, weak electrolyte. We just looked it up, it's a weak electrolyte. Strong electrolyte, weak electrolyte. It's cesium. Strong electrolyte. So now, the total ionic equation. Break it apart. What do you got? 2 Fe plus 3 aqueous plus 6 Cl minus aqueous plus 6 Cs plus aqueous plus 3 SO3 minus 2 aqueous to give me what? Do I break this one apart?
No.
Nope. Fe2 SO3 3 solid plus 6 Cs plus aqueous plus 6 Cl minus aqueous. Do I break apart anything else? No, I did it already. And now what do I do? I
Then
cancel out what? What are they called?
Spectator.
Spectator ions. Do I have any spectator ions? Yes, I do. Cesiums and chlorides. Big. So when I rewrite for the net ionic equation, what do you got? 2 Fe plus 3 aqueous. Shh, guys, settle down. Plus, I cancel these two. 3 SO3 minus 2 aqueous. So give me what?